What would it take to stay alive on Mars if everything suddenly started to fail? Imagine this. You're part of the first human crew on Mars. Your habitat, built over years of careful planning, is the only barrier between survival and the lethal Martian environment. Then, something goes wrong. Power systems fail, oxygen levels drop, water recycling stalls. The red planet turns hostile. What do you do when your life support fails 225 million kilometers from Earth? Survival on Mars isn't just about bringing the right equipment. It's about knowing how to adapt, improvise, and recycle resources in a closed-loop system when redundancy fails. Let's walk through what a power failure might look like and how a crew might respond in stages. First, power failure. On Mars, most habitats are designed to rely on solar panels, supplemented by nuclear batteries like NASA's RTGs or next-generation fission reactors. If solar arrays are damaged by a dust storm or if backup systems glitch, energy suddenly becomes precious. Everything from lights to oxygen pumps depends on it. The first step would be to prioritize life support functions. Power would be diverted to oxygen generation, CO2 scrubbing, heating, and communication. Non-essential systems, labs, kitchen appliances, recreational devices, would be shut down. If a nuclear backup is present, the crew might attempt to reroute power through manual overrides or deploy mobile battery units. Next, oxygen deprivation. Mars has 0.1% of Earth's atmospheric pressure and virtually no breathable oxygen. Habitats rely on electrolysis systems that split water into hydrogen and oxygen, or solid oxide electrolysis units that extract oxygen from the CO2-rich Martian air. In a crisis, portable oxygen tanks or emergency oxygen candles, chemical compounds that release O2 when burned, would be the first line of defense. By time, astronauts might seal off smaller compartments to concentrate breathable air and limit physical activity to reduce oxygen consumption. Stretching a limited supply could mean surviving an extra 24-72 hours, just enough to bring a backup system online or perform external repairs. Then, water and resource recycling. Mars settlers can't afford to waste anything. Water is reclaimed from urine, sweat, and even exhaled breath through advanced filtration systems. In the event of a failure, the challenge is to prevent system contamination and minimize water loss. Emergency rations would include condensation kits, manually pumped filters, and stored reserves frozen beneath the floor panels. Astronauts may also melt collected subsurface ice if they're near an ice-rich region, though this requires energy and filtration. Food is less immediately urgent. Humans can survive weeks without it, but maintaining a biosphere or hydroponic garden becomes critical if the failure is long-term. Plants not only produce food, but recycle CO2 into oxygen. If lighting systems die, astronauts might repurpose suit mount lights or reflectors to sustain key crops. In extreme scenarios, they could also rely on insect-based protein or freeze-dried reserves. Beyond logistics, there's the psychological challenge. Isolation, the creeping cold, rising CO2, and the hum of dwindling systems constrain even the most prepared minds. That's why every Mars mission includes mental health protocols, simulated crisis drills, and AI-assisted monitoring systems that provide guidance during emergencies. Even simple tasks like journaling or talking to Earth, even with a 20-minute delay, can ground a person when reality feels like science fiction. But here's the remarkable part. Humanity is already planning for these scenarios. NASA, ESA, and private space companies like SpaceX simulate Mars emergencies in analog environments, underground caves, Antarctic bases, and desert habitats. Engineers study how to patch life support systems using duct tape, how to hack power from solar panels in a storm, and how to revive CO2 scrubbers with makeshift chemical reactors. So, can a crew survive a spacecraft failure on Mars? With the right training, modular equipment, and calm decision-making, the answer is yes, at least for a while. The key is redundancy, resilience, and rapid response. On Mars, every breath, drop of water, and watt of power counts. And surviving a dying colony means not only having the tools, but the will, and knowledge to adapt when systems and expectations collapse. Because in the end, space doesn't forgive mistakes, but it does reward those who prepare for them. The Martian Survival Paradox refers to the dire and fascinating situation in which a human colony on Mars faces catastrophic failure, power loss, oxygen deprivation, and resource exhaustion, yet survival must continue using only the degraded components of the failing system. This scenario contradicts our expectations of survival as a function of abundance and redundancy. Instead, it reveals how life can be prolonged through improvisation, system repurposing, and the creative use of residual energy and materials in a closed, decaying habitat. In simulations, astronauts on analog Mars missions have survived simulated life support failures by rerouting oxygen from reserve tanks, manually melting ice for water, and using chemical CO2 scrubbers without power assistance. It's like being locked in a frozen vault with only the scraps of yesterday's technology and discovering that survival means turning the wreckage into a new kind of life support. A Martian base relies on a tightly coupled network of life-sustaining systems: power generation, solar or nuclear, oxygen production via electrolysis or chemical loops, water recycling, temperature regulation, and food processing. In case of a failure cascade, one system's collapse often drags others with it. Survival depends on the ability to decouple and isolate subsystems and create minimalist, manually operated versions that prioritize only what is essential: breathable air, thermal stability, and hydration. When a solar storm disables photovoltaic arrays, crew members may isolate essential habitat sections, use battery reserves for heating, and initiate chemical reactions to generate oxygen from perchlorate compounds in the Martian soil. Imagine a luxury cruise ship sinking. Survivors do not need the ballroom, but a lifeboat with clean water, oxygen, and insulation. Mars survival is that lifeboat, jury-rigged from the hull of the sinking ship. System failure on Mars often begins with a primary disruption: energy starvation from dust-covered solar panels, circuit overload, or equipment degradation. The breakdown disables CO2 scrubbing, halts oxygen regeneration, freezes water pipes, or kills thermal control loops. Countermeasures must occur in real time, using manual overrides, repurposed materials, and closed-loop chemical processes that can operate passively or with minimal energy. Using lithium hydroxide canisters designed for emergency CO2 removal, crew members can delay asphyxiation long enough to repower key systems or retreat into a smaller, better sealed habitat zone. It's like using a tea kettle and candle to warm your last room during a blizzard. The goal shifts from comfort to survival through minimalism. A dying Martian colony is a case study in systemic collapse within tightly coupled engineered environments. Under normal operation, efficiency and automation dominate. But during failure, complexity must be reduced. Human operators must become part of the control loop, manually enacting functions usually governed by software and sensors. The system becomes semi-biological, relying on the intelligence and improvisation of its inhabitants to mimic the lost functionality of machines. When automatic nutrient circulation fails in hydroponic modules, astronauts manually harvest plants and irrigate them using stored condensation and body heat. It's like replacing a circulatory system with hand-pumped syringes. Life continues, but with muscle and ingenuity, replacing silent circuits. When power is scarce, it must be allocated to vital, non-negotiable needs. Heat, oxygen, and communication dominate. Everything else, lighting, data logging, mobility, becomes secondary. Often the strategy includes energy scavenging, rerouting residual charge from non-critical systems, converting waste heat, or using low-tech chemical processes to substitute for high-power equipment. Every joule becomes sacred. In one concept scenario, urine is processed via passive osmosis membranes to reclaim water, while exothermic chemical packs warm water stores during heating system failure. It's like dismantling the family car to keep a candle burning. It is the final accounting of what energy is and what it is for. As critical systems fail, information becomes as vital as oxygen. Communication with Earth lags by up to 20 minutes, and autonomous decision-making becomes paramount. Survivors must process massive information under pressure, choosing which sensors to trust, how to interpret data manually, and when to make irreversible calls. Cognitive load, not physical resources, becomes the true bottleneck. NASA's Mars analog missions train astronauts to operate under decision delay, simulating loss of feedback and forcing crews to act without confirmation. It's like playing chess blindfolded, with pieces missing and the clock ticking. Your moves define the next 5 minutes of breathable air. This paradox extends beyond Mars. It teaches that survival on other worlds hinges not only on technology, but on the philosophy of systems design, redundancy, repurposability, and human agency. Ethical questions emerge. Who decides resource allocation? What happens when air must be shared but not all can be saved? These scenarios shape our approach to resource scarcity, crisis response, and life extension on Earth. Concepts like survivable minimalism and regenerative autonomy now influence climate adaptation shelters and disaster-proof hospitals. It's like learning to garden inside a submarine. You grow a future with barely enough light and no second chances. Even the best simulations cannot capture the moral weight and psychological stress of real collapse. Models break down when confronted with fear, fatigue, or interpersonal breakdown. Survival on Mars requires not just engineering excellence, but emotional resilience, creative problem-solving, and social cohesion. As machines fail, the human mind becomes the last operating system. Long-duration analog missions like HISES and MDRS show that, even with resources intact, isolation and conflict can derail survival protocols. It's like surviving with only 3 people in a dark maze. If one loses hope, the light dims for everyone. The future of Martian survival design lies in modular self-healing systems, human-in-the-loop control, and biohybrid redundancy, where plants, microbes, and human routines reinforce synthetic systems. From oxygen-generating algae to heat-storing biopolymers, Mars becomes a testbed for Earth's most extreme sustainable living. Survival, once defined by strength, now depends on adaptability, collaboration, and humility in design. NASA and ESA are testing backup life support modes that mimic bacterial respiration, soil insulation, and plant-based CO2 cycling, designed to fail gracefully rather than catastrophically. It's like building a violin that still plays when half the strings snap, because the melody of survival must continue, even in silence.